Welcome to 747 Review. We're going to go through the flight engineer's panel, the overhead panel, and the front instrument panel and review the major systems on the 747. This is in no way intended to change or abridge any of the procedures that your handbook puts out. This is simply a systems review on the various systems of the airplane. I'm going to start down here at the bottom of the second officer panel and talk about the breather temp gauges. The gauges represent the temperature in the gearbox of the engine. There's been problems with air bypassing the various bearings in the engine and finding its way into the breather box and getting the oil so hot that they've had a few what they call oil box fires. These temperatures monitor that and indicate when that problem exists. Next is the filter bypass. The filter bypass operates on the oil filter if contamination exists and plugs up the filter, causing it to go around the filter, indicating that there's probable damage to the engine. Normally the filter bypass light comes on when the engine is running and contamination exists. The engine should be shut down. However, on a very cold morning where the engine is cold soaked, the filter bypass light can come on, and this would be due to the difficulty of the oil getting through the filter. However, as long as the oil temperature is coming up, then it's permissible to have the filter bypass light on and continue operating the engine. Normally the taxi out time should be sufficient to warm up the oil and the filter bypass light goes out. If this does occur, engine operation can continue, however a logbook write-up should be made. Oil pressure. Oil pressure is monitored during engine start and should be in the green band by the time the engine reaches idle. It is permissible to operate for a period of time the engine below the green band in the caution band for ground operation. However, for normal engine operation, it should be in the green band. Anytime the engine oil pressure is above the green band or below the red radio, the engine should be shut down if it isn't necessary for safe operation of the airplane. In association with the oil pressure gauge, there is a oil pressure light on the front instrument panel. These two sensors require different power supplies, so the loss of one will not affect the other. One of the problems involved with the oil pressure gauge is with a gauge failure, the pointer will remain in position. So it's difficult to tell whether the oil pressure is proper or not. However, if the oil pressure light up front is on with the pressure in the green band on the gauge, a engine shutdown should be considered. Oil temperature is recorded as the oil goes into the fuel system. Normally, the oil temperature will be reading ambient prior to engine start, and as the engine starts, it will come up to approximately the 9 o'clock position. Operation in the caution band is allowable for a period of time due to the oil being cooled by the fuel going into the engine. By adding thrust the oil temperature will drop slightly until the engine warms up and then come back to normal. Likewise, when pulling off thrust, the oil temperature will rise due to less fuel flow and then come back down to normal. Because of the rise, it could operate in the caution or amber band for a period of time. Of course, anytime the oil temperature gets into the red band, the engine should be considered for shutdown. One thing that may cause the oil temperature to go into the caution band and stay there is operation of engine fuel heat for a period longer than 3 minutes. And this would be accentuated by turning on the fuel heat and then pulling off the thrust. Both less fuel flow and the fuel heat would cause it to go into the caution band and stay there. Anytime you have abnormal oil temperature in the caution band, one of the first things to be considered would be to check that the fuel heat on that particular engine is off, and going to the fuel panel, making sure by selecting that engine what the fuel temperature is. The fuel temperature with fuel heat on will generally make the meter read at 60 degrees or higher. Pegs out the meter. One of the solutions, if the fuel valve is stuck in the open position or does not properly close, is quickly move the fuel heat switch to open and then back to close again. You might try this several times. And of course, if it does not bring this fuel temperature back down into the green band, the engine should be considered for shutdown. Oil quantity. Generally, the oil quantity gauges will drop a sufficient amount on engine start, generally between a gallon and a gallon and a half. This is due to the scavenging system of the engine and does not indicate any kind of oil leak. It is a normal type operation. However, after the engines are started, it is a good idea to record the fuel quantities, and this will give you a good base to determine the engine fuel the engine oil consumption. One thing that's unique on the oil quantity gauge, if the gauge should fail, the pointer will be brought completely off the scale to a portion that is labeled off. This way you can differentiate between total loss of oil quantity and a failed gauge. N2 gauges. The N2 gauges are powered gauges. They are not true tachometers. They require electrical power from the aircraft. With loss of the power, the pointer will go to zero and a flag will drop across the digital readout. In addition, the gauge has a max pointer which lies over the red radio, and if for some reason the engine should overspeed, the pointer will move the max pointer to the maximum value at which the RPM has been reached. And this removes any discussion about how high the RPM went. Any one of these four gauges can be reset by a master reset on the center instrument panel, which also at the same time resets the EGT gauges and the N1 gauges. Next, we're going to talk about the generating electrical system, starting with the CSDs. The CSD indicator indicates both the out temperature and the rise temperature. The out temperature is the upper portion of the gauge starting at 50 degrees going clear to the top of the scale. The rise temperature starts at 0 and goes to 30. Normally you're looking at the out temperature. If you wish to look at the rise temperature, there is a CSD temp rise button, which upon depressing the button causes all 4 gauges to look at the rise portion and read on the lower portion of the scale. Now the 2 parts of the scale represent 2 different types of operation of the CSD. The out temperature indicates the ability of the air, which uses fan air, to cool the CSD oil. And it tells you how well that's working. On the other hand, when you push the button and you're reading rise, this indicates the difference between the out and the in temperature. And this represents how hard that CSD is working. In a way, it indicates the torque ability or the difficulty it has in trying to operate the CSD. The difference being the out temperature indicates that the CSD total oil system is operating at whatever the pointer is operating. 2 things could cause these temperatures to read abnormal. One is a low oil quantity. A low oil quantity would make the oil circulate faster, not have enough time in the cooling radiator, and make it operate at a higher temperature. 2, the internal operation of the CSD itself, either through mechanical or hydraulic operation, excessive clearances and so forth, could make it work much harder than it is necessary to operate the CSD. The net result is when you're operating at too high of a temperature, either the out or the rise, imminent failure to the CSD is possible. To prevent this from happening, a disconnect switch, which is normally safety wired, located just above it, can be operated to totally disengage the CSD from the accessory drive. When this happens, or when you want to operate the disconnect switch, you should select the generator you wish to disconnect with the AC meter panel and hold the generator test. Upon activating the disconnect switch, you will see immediate drop in RPM and PMG of the generator. And if the low pressure light was not already on, that should also come on, assuming engine is running. If the disconnect switch is operated with the engine not running, the CSD may not disconnect right at that instant, but as soon as the engine starts, it will disconnect. So anytime the safety wire is broken, it should be investigated and made sure the CSD is properly attached prior to engine start. Generator bearing failure lights are strictly a generator problem. It indicates that excessive clearance is in the bearings at each end of the generator. They may come on steady, they may glow, or they may blink at you. In any case, it means the bearings are allowing excessive play in the generator as it's rotating. Generator bearing failure light coming on is also a good reason to disconnect the CSD. Field switches. Field switches are off-on switches for the generator. When the switch is tripped, if the generator breaker is also closed, it will trip it. When the switch is closed, it makes that generator available to operate an electrical load. Of course, when the engine is shut down, the field will stay closed. However, the generator is not available unless the engine is operating at idle or higher RPM. KW meters. They represent the power that is being operated or taken out of the generator at any particular moment. Also, they can also indicate the amount of KWs that are being operated from that particular generator. by operating a push-button switch just to the right of the last meter. The kWs represent actual work. The kVARs represent balance between operating generators. The value of the kVARs is not of particular importance, but when generators are operating in parallel, the balance between the highest and the lowest indicate how well the generators are operating together. If they get out of balance too far, automatic protection will isolate that generator by opening the bus tie. If that opening the bus tie represents a further electrical problem with the generator may cause the field trip, the generator breaker to trip, and the bus tie to automatically close again. Anytime any automatic action takes place with the generators, it will be represented over in this portion of the engineer's panel by a light coming on here when the read button is depressed. One very important thing about this particular panel, no light will ever illuminate on this panel unless you're holding the read button. The read button must be depressed to indicate. Normally, flight crews do not erase the readings on these panels and leave them remain on for further troubleshooting by the mechanics that fix the problem. The flow of power is very nicely laid out by a Boeing schematic here of each of the 4 main AC buses on the airplane. The engine drives the CSD, which operates the generator, which goes through a meter, through a generator breaker switch to supply power to an AC bus. The AC bus can also be supplied through a tie bus from any of the other operating generators, or APU, or ground power. In addition to the normal AC buses, we have the essential bus. The essential bus normally comes off of AC bus number 4. However, if there is a particular problem, a short on bus number 4, essential power can be manually selected to come directly from generators 1, 2, or 3. Or, if there is a short on the essential bus can be selected to off, thereby killing the essential AC bus and not causing a large electrical load on bus number 4 or generators 1, 2, or 3. Essential power in normal can be fed from any one generator through the tie bus, or directly from bus number 4, from generator number 4, or from ground power, or from APU power, without moving the selector switch. Under normal operating conditions, essential AC power should be available in a normal position unless you have loss of all generators. No need to switch essential power as you switch types of power from ground power, APU, or aircraft power. At the top we have bus tie breakers. These are to connect the aircraft generators and the aircraft buses together. There's many automatic protections on it, and there's no way you can override an automatic protection. If the automatic protection says it's no good, you can hold the switch up, it just won't operate. Normally, prior to engine start, the fields are closed and the bus tie breakers are closed and the generator breakers are open. And power is coming in the aircraft either from ground power, external power number 1, through the tie bus into each of the 4 AC buses, or from auxiliary power unit APU, which comes in through this way, through the same tie bus to each of the 4 buses. I'd like to talk now about the ground power. We have a ground power connected light here. Actually, there's 2 ground power units, plugs in the belly of the airplane, right by the nose wheel. And when the power is plugged in, this light will illuminate. Very seldom is external power 2 used. External power 1 is always used for a reason I'll explain in a minute. When ground power is plugged in, you can monitor and check to see the proper voltage and frequency is of the correct value by coming down to the AC meters panel and pushing the button external number 1. And even prior to coming in the aircraft, you can read the frequency and the voltage to see if it's within limits. If it is, upon moving the switch to close, the green light will come on and power will be applied to the tie bus. Now, using number 1, power will be immediately applied to bus number 1 and bus number 2. However, if this split system breaker is open, green light on, power will not be on bus number 3, number 4, and essential power. So applying ground power, make sure the voltage and frequency is correct, and bus tie breakers are closed, and the split system breaker can be closed. Now, the amount of power that's being used by ground can be measured in amps with this meter. If auxiliary power unit was wanted and the APU is running, upon closing the field on the APU, the field off light goes on. You can come down here and select APU generator number 1 and check the voltage and frequency, even when ground power is still feeding the aircraft. Then, if you selected the switch for the APU to close, it would automatically trip off the ground power. The green light would go out, and the amber light for the generator breaker of the APU would go out, and all the systems that were previously being operated by external power will now be operated by APU number 1. If you wish to use the second APU generator, which is normal operation, again, closing the field on number 2 APU generator, you come down here, select number 2 APU meter button, and you can check the voltage and frequency on it. If it was proper, upon closing the generator breaker and APU, the first thing that would happen would be the split system breaker would automatically trip, and then the generator breaker would close. The amps would drop on the number 1 meter, and amps would come up on number 2, and buses 1 and 2 would now be powered by APU number 1 generator. Buses 3, 4, and essential power would be powered by APU number 2 generator breaker. At all times, ground power number 1 should be used, or APU number 1 should be used, because there is a special ground handling bus which is powered when these power sources are operated. The ground handling bus is specifically for ground operation, and there's several very important things that are on that ground handling bus. One being operation of the cargo doors. The cargo doors cannot be operated unless ground power is plugged in or the APU is running and the number 1 APU field is closed. The ground handling bus is automatically powered when either one of these 2 conditions exists. Another very important thing that's on the ground handling bus is operation over here of the electric hydraulic pump for backup brake for operation when the engines aren't running or pneumatic air is not available. The electric pump over here will operate off that ground handling bus. The electric pump will not operate off aircraft systems. It's only available when ground power is plugged in or the APU is running. And the split system breaker is a very unique item, and it has many automatic functions to trip, but it has no functions that will make it automatically closed. If you want the split system breaker closed, the operator must move the switch to close. Now, when he moves it to close, it may or may not close, depending on whether conditions are correct. The only time the split system breaker will close is when the other side of the bus has no power on at all, or you are paralleling it with other aircraft generators. The split system breaker will not close with connecting the two APU generators or ground power or any combination of it. Now, many things will make it trip, but nothing will make it automatically close. Next item I want to talk about is the APU itself. In operating the APU, when you first turn the switch on, if a fault light appears, there's no way you can start the APU. You may have to move the switch back to the stop position, and if the door is partially open, the door has to go through a full cycle and close prior to being able to start the APU. On moving the switch to on, if no power is available on the aircraft other than the aircraft battery, you will see a DC pump on light illuminate to supply fuel from the number 2 tank to operate the APU. If aircraft power is available or ground power is available, the DC pump on light will not illuminate, and the fuel will come from the number 2 main tank with the number 2 aft boost pump pressure light going out. If the pressure light does not go out, then the green light will come on to supply the fuel pressure. The DC pump is intended to be an intermediate duty pump to operate only up to the point that you can get the electrical power on the airplane from the APU. Fuel valve will also operate a very short period of time by a blue light coming on for a period of 2 to 3 seconds and then going out. And anytime the APU door is in operation, the blue light for the APU door will come on. On the ground, this takes approximately 30 seconds, and in flight it's about half that time. Once the door is open, the APU can be started. And upon holding the switch to the start, which is spring-loaded, you will see RPM, and then after a short period of time, EGT. Generally, during the start, the oil quantity will drop. If it drops into the red band, the start switch should be placed to stop immediately. There are quite a few items that will automatically shut down the APU, but in every case, anything that automatically shuts down the APU fault light will illuminate. And of course, you would expect to see the RPM and the EGT to drop also. Prior to starting the APU, a fire test should be done. The APU has 2 fire detection loops, the A loop and the B loop. Either one of the loops by itself could cause the APU fire light to come on, and in all cases, the APU should automatically shut down when the APU fire light comes on. The exception to that is if you're doing a fire test. On doing a fire test, it bypasses the automatic shutdown, and the APU will not shut down on a fire test, but will shut down on a fire warning. The APU fire switch, if a fire should occur, has already shut down the APU and would have also operated the fuel shutoff valve. So essentially all you do when you pull the fire switch is arm the bottle discharge to discharge the Freon into the APU. The Freon bottle is located alongside the APU back in the tail of the airplane, in the unpressurized portion of the airplane. One other thing I'd like to mention about the APU fire system. If an APU fire light is illuminated with the APU shut down, I would consider pulling the fire switch and discharging the bottle. Next panel I want to talk about is the passenger oxygen. We have an oxygen gauge here with two pointers in. This is a combination of the passenger and the crew oxygen. The passenger oxygen is the one with the red pointer, and the crew is the one with the black pointer. Normally you'll find the black pointer somewhat less than the red pointer because each crew that gets in the airplane checks out their mask and uses up a little oxygen. However, the passenger oxygen shouldn't drop at all unless it is required for some sort of emergency. Alongside of it there is an on light, and there's also another light that operates off the same system on the master enunciator panel and the center instrument panel. Either light will come on at the same time when the system is pressurized. Pressurizing the systems will drop the doors, allow the mask to fall out, and if the passenger pulls the mask towards his face, allow the use of oxygen. The system is pressurized by one of two methods. Normally, it is not used in case of an emergency when the cabin pressure is lost, and if the cabin altitude goes above 14,000 feet, it's automatically displayed. There's a little next to stop it from being displayed. However, at any time below 14,000, if it's desired to present the mask to the passengers, a switch here can be operated that will electrically display the mask and pressurize the system. It should be noted that at the lower altitudes, generally below 10,000 feet, very little or no oxygen will be supplied to the system, even though the masks are displayed. At the higher altitude, barometric control will meter the oxygen for the various altitudes. Galley power has 4 switches. Each switch is associated with its AC bus. The 1 and 3 switches are for the forward galley, the 2 and 4 switches are for the aft galley area. If an electrical short should occur, the galley will trip off and the trip-off light will illuminate. Sometimes this can be reset by simply turning the galley switch off and then back to on. If cycling it off back to on and the trip-off light remains on, then maintenance should investigate to find out what the problem is. Below this we have a 3-mode generator switch. The 3-mode generator switch is left in the normal position. If less than 4 aircraft generator breakers are, if 4 generator breakers are not on the tie bus and aircraft buses, in other words, the generator breakers are not closed, the generator mode will go into the 3-mode operation, which upon reaching large electrical loads will start shedding off various devices. This is done automatically. If you wish to override this function and override position is in the upper position, and it will put out the 3-mode light. It is normal for the 3-mode light to be on when ground power or APU power is being operated, because not all 4 generator breakers are closed. Alongside of it, but not in association with the 3-mode generator, is another switch called the Galley Lav Fan switch. In automatic, it operates at lower cabin pressures, and as you get to a higher and higher altitude, when the pressure differential in the aircraft on the pressurization gets approximately 6.8 psi, this Lav galley vent fan will stop and open another overboard vent in the middle of the fuselage. And then as you descend in altitude and the pressure differential comes down, it will start up again. The vent system is exactly what it says. It's to remove odors from the galley and the lavatories when low pressure differential is in the airplane. So on the ground and at low altitudes it's operating all the time. If you wanted to operate at higher altitudes, you can take it out of auto and put it on, and the vent fan will operate under all conditions regardless of the pressure differential. Likewise, by moving the switch in the off position, you will turn the Lav galley vent fan off and it will not operate at all. Below the Lav galley vent switch, we have the DC isolation switches. There's a schematic here showing how they connect the DC isolation buses together, and warning lights to indicate whether the switch is open or closed. Normally the switches are closed under all operating conditions and the lights are normally out. One thing I might say about the DC system, it's a relatively trouble-free system, and to lose a bus you would generally have to lose the entire electrical system. In other words, as long as one DC TR unit is available, it should be able to feed the other DC buses. The one exception to that is on some aircraft, the Essential bus has a blocking diode that will make the Essential bus available only for the Essential DC bus and not for the other DC buses. However, any one of the DC buses 1, 2, or 3 can and will feed the Essential DC bus, but not backwards. On some aircraft, this blocking diode has been removed. And if Essential power is moved out of the normal position to either generators 1, 2, or 3, and that generator is available to feed Essential AC power, the number 3 DC isolation switch will automatically come open and the light will come on. The switch itself will not move, but the light will come on and it will effectively divide the DC bus so that buses 1 and 2 are connected together and buses 3 and Essential are connected together. If Essential power is moved back to the normal position, the bus will automatically close. Next item I'd like to talk about is the battery switch. The battery switch needs to be in the on position for all aircraft operation. Normally it's turned on when the second officer sits down in the seat, and it's turned off when he gets out of the seat to leave the aircraft. However, the battery itself is not normally operated unless there's no other source of power available to the aircraft. It's a backup source. And when the switch is put to the on position, it really doesn't supply battery power, but simply allows the battery to be used in the backup capability in case of loss of all generators or loss of ground power, etc. To determine whether the battery is supplying power or actually being charged, which is normal, you select a battery switch here, and it makes the two DC meters read off the battery. Under normal circumstances, the battery voltage will be reading between 27 and 30 volts, and the ammeter will be reading between 0 and some plus value, indicating the battery is being charged and not being operated. If loss of all generators or battery-only power is available, the battery voltage would drop down around 23 to 24 volts, and the DC amps will drop down between 0 and minus 50. And this would indicate the battery drain. Boeing indicates that the battery should be available with loss of all generators for a minimum of 30 minutes. However, one of the items that is on that battery bus is the #1 COM transceiver. And if you're making radio reports, every time you use the radio, you're going to reduce the amount of time that that battery is available. So it could be considerably less than 30 minutes if you're using radio a lot. Likewise, on selecting the other DC buttons, you switch the 2 meters to that particular unit. And for example, if you selected Essential TR, the voltage and the amps being used from the Essential TR would be reflected. And the amps would indicate plus when the TR unit is supplying those amps. If the TR unit should fail, the amps would go to 0. However, the voltage would remain normal as it is being fed through the DC tie bus from any one of the other TRs. So the difference is the DC amps is reflecting the output of the TR. The DC volts is reflected the voltage on the DC bus. One may be working without the other. By the way, if you should happen to, I'm still pushing on it, if you should happen to turn the battery switch off when the APU is in operation, the APU will shut itself down. The APU requires the aircraft battery switch on to ensure that the automatic protection devices for the APU are available even if the APU generators are not operating. Next item I'd like to talk about is standby power. Standby power is a bus that supplies key important items on the aircraft. Some of the captain's instruments, the ability to relight the engine in flight, some of the engine anti-ice valves, etc. With the switch in the normal position, if essential power is available, both AC and DC, the standby buses are powered by the essential buses. However, with the loss of essential power, standby power will automatically switch to the aircraft battery bus and is available to be fed off the aircraft battery or anything that's feeding the aircraft battery bus. And this assures that under just about any electrical condition that could happen to the aircraft, that the standby AC and the standby DC buses are available. Now, since the power is coming from the battery, the standby DC just requires a relay to close to power that bus. However, standby AC has to be generated through a black box called the standby inverter. And the standby inverter operations is indicated by a green light coming on. If, in loss of all generators, the green light does not come on, then the switch should be moved to the manual on position to see if that would work. And of course, if it doesn't work in any position, you're not going to get it. It's gone. Also, the manual on position is used to check the standby inverter for pre-flight on cockpit setup. I'm moving the switch from normal to manual on. the green light should come on, and the flight engineer should check the center instrument panels to see if the EGT and N1 gauges are operating and flags are not displayed. Since these instruments require AC power, if the standby inverter isn't working, then the flags would be displayed indicating that the standby inverter was inoperative. Now, there's other items on the bus, but these are the most reliable items to check to see if the standby inverter is operating. Alongside the standby inverter is the central power selector switch. We discussed that a little bit earlier. However, anytime essential power should be lost, an essential power off light will come on the engineer panel, and also one in the center instrument panel, indicating that bus is not available. Selecting generators 1, 2, or 3 will put the essential bus directly on the output of the generator. The way I like to think about it is it's coming right out of the meter before the bus. And you will see a reflection of that load in the meter if it was selected. The essential power takes a very low amount on the load meter, essentially 2 or 3 kWs, which is a very small amount, about approximately a needle width. Alongside the standby power switch, there's an INS battery parallel. On some aircraft which has only 2 INSs, this switch is deactivated. On aircraft with 3 INSs, it allows taking the number 3 INS battery and put it in parallel with the number 1 INS battery to allow the number 1 to operate with loss of all generators or no power on the bus for approximately twice as long. The INS battery normally should be able to keep the INS running for approximately 15 minutes. However, when you parallel it, you can keep the number 1 running for approximately 30 minutes. However, once you operate this switch and move the battery off INS number 3 onto INS number 1, the INS number 3 is inoperative and can't be used anymore, even if after power is restored. Another thing it requires this switch to operate is the standby power green light to be on. On the bottom row here we have AC meters selectors. So you have one for each of the 4 generators, and we have one for APU number 1 and number 2, and external number 1 and number 2. On the far left, on the bottom row, there is a test button, and when you push this button, it changes the inputs to the frequency meter to RPM, and it changes the inputs of the voltage meter to PMG. PMG is permanent magnet generator, and it reflects the speed at which the generator is turning. Now you might say, well, if the CSD is turning, the generator's got to be turning. Not necessarily so. There's a drive shaft between the two, and if that drive shaft should shear, then the CSD can be working perfectly normal and have normal RPM, and the PMG would be reading 0. Also, the PMG does not read on external power. The RPM does not read on external power. The RPM does not read on APU, but the PMG does read on APU. Remember, anytime you want to read RPM or PMG, the button must be depressed. As soon as you release it, then it reverts back to the RPM to frequency and PMG to volts. Normal position for these gauges is 9 o'clock position. Generally, anytime you can read the frequency or the voltage on the gauge, the generator breaker will close. However, it may be beyond operating limits, and continued operation off frequency or off voltage could cause damage to the more sensitive equipment on the aircraft, particularly the avionics. The next panel I'd like to talk about is the pressurization control panel. Starting with the mode selector switch in auto. Automatically, the outflow valves are controlled in auto by two separate channels, one for the left outflow valve and one for the right outflow valve. However, in auto, anytime you're on the ground, the outflow valves will be at the wide open position, which is controlled by the ground safety relay green light being on. When the ground safety relay light goes out after takeoff, the outflow valves will do whatever you have set in for the pressure controller. The check position overrides the ground safety relay, allowing the outflow valves to be closed on the ground. In other words, it bypasses any input of the ground safety relay. And the outflow valves can be closed on the ground by running the cabin altitude below field elevation. When you go to the manual position, manual will put control of the outflow valves to the two toggle switches, and you'll be able to operate the outflow valves through operation of the toggle switches. One thing I'd like to point out here is in auto, the outflow valves are operated by AC motors, which is somewhat quicker than manual. When you go to manual, the outflow valves are operated with the toggle switches, which receive power from the battery, aircraft battery. And of course, anytime you're in an aircraft, the battery switch is on, so the outflow valves should be operable. The rate knob will control the rate at which the cabin will climb or descend, and normally it's left in the PIP position, which is the 9 o'clock position. That will allow approximately 400 feet per minute climb or 300 feet per minute descent. When the knob is full counterclockwise, this could limit the rate of climb or descent to 50 feet or less. Now, no matter how good the outflow, the pressure controller is doing a job, it cannot pressurize the airplane unless air is coming in the airplane from the packs. The auto fail light will come on from power glitches or excessive rate of climb or descent. When the auto fail light comes on, it takes the control away from the two auto controllers controlling the left and right outflow valve and puts it in the hands of another controller, which will automatically try to maintain the cabin pressure. The outflow valves will oscillate, and the cabin rate of climb will go as high as 1,000 feet per minute up and down, and the cabin itself will gradually pressurize under the auto fail mode. To get control back again from the auto fail mode, the mode selector has to be moved out of auto into manual. That will put the light out. Now, it's a possibility you could go back to auto again and operate under auto. If that isn't available, then you would have to go to manual, manual left, or manual right. The difference between manual and manual left and manual right is when you go to, for example, manual left, the left outflow valve is under control of the toggle switch. The right outflow valve is still under control of the auto controller. The advantage of this is if something is wrong with the auto controller on the left outflow valve, you can toggle the left outflow valve to approximately 1/8 from full closed and allow automatic operation on the right outflow valve for climb, cruise, descent, landing, etc. And it will do a good job. You don't have to sit there and control the rate of descent with the outflow valve. One other point I'd like to bring out is the auto controllers are somewhat faster than manual controllers. The operation of manual controllers is quite slow because it uses different motors. The auto controller uses an AC motor, and the manual controller uses a DC motor, which is controlled by the battery. Moving up to the pressure relief lights, pressure relief valves relieve air out of the forward cargo into outlet at the left side of the airplane, just forward the leading edge of the wing. There's two of them, and they are not connected to each other. They relieve the pressure in the aircraft around the red radio on the pressure differential gauge. Since they are individual, they may not both operate at the same pressure, so it only takes one to relieve pressure in the airplane. And when it does relieve pressure in the airplane, the duct pressure, the differential pressure, will drop several pounds before it can build up again. It will reset at a much lower value than where it originally trips. The next two gauges, the cabin altitude and the cabin rate of climb, are non-electric gauges, and they will reflect what's happening in the cabin. Going up. Okay, let's talk about the pneumatics now. We have a pneumatic duct pressure gauge here, which senses pressure from the left and right side of the pneumatic duct. We have 4 engine pneumatic bleeds. Physical location is in the pylon of the engine. We have 2 isolation valves, which cut the air out, going out to the wing on the left and right side of the belly of the airplane. And we have 3 pack shutoff valves. To get the whole system all together, I'd like to show you a little diagram and go through the items that are operated off this pneumatic system. Over here I have a little sketch of the entire pneumatic system. And starting with the basic source of air, we have the 4 engine bleeds. The air coming out of the engine comes from 2 different sources, high stage and low stage air. The low stage air is used most of the time. However, under low engine thrust, the low stage air does not provide enough air to maintain pressurization in the aircraft, so an automatic device switches in high stage air. When the high stage air comes in, this comes in at a time when the throttles are reduced. Normally it's necessary for descent. If the high stage air does not come in, then the low stage air would allow the cabin to climb when you're trying to descent rather than pressurizing it, bringing it down to airport elevation. The air coming out of the engines are controlled by 4 bleed valves. Now the bleed valves have a simple control knob on the panel. However, they are not simple devices. They have a great deal of automatic control functions to them. Directly downstream of the control valve, there are 4 air-driven pumps, and it taps the air in the pylon downstream of the bleed valve. Of course, there is a control valve for each of the air pumps, so you can operate them or turn them off. This comes into a large duct that goes practically from wingtip to wingtip and through the center portion of the unpressurized portion of the airplane, represented by what is called the pneumatic duct. The items that are fed off this pneumatic duct are essentially the wing anti-ice on the left and right side, the 3 air conditioning packs, the wing leading edge flaps, the pressurization of the water, drinking water system, the aft cargo heat, and the items that can feed the duct other than the engines is pneumatic air from the APU and the hookup of the ground cart, which comes in between the two isolation valves. Now, if both isolation valves are closed, then in flight, the use of pack number 2, the water pressurization, the cargo heat, is not available. If ground power or APU is used, then with the isolation valves closed, only pack number 2 can be operated, and the cargo heat and water. Of course, these two you won't care about on the ground. On operation, normally the isolation valves are open, and they are only closed with a pneumatic leak or a problem where you want to boost pneumatic pressure up. The duct pressure gauge reads the left and right wing pressure. There's the dual gauge. Of course, if the isolation valve is closed, the gauge may be different from the left and right side, but normally they're open and one pointer lays on top of the other and they all read the same thing. In review, I want to cover again the items operated off the pneumatic system. The leading edge flaps, left and right side, the wing anti-ice, left and right side, the 3 packs, the air-driven hydraulic pumps, the pressurization on the water system, and the cargo heat. This is aft cargo heat only. The pressurization on the water system is not totally relying on this pneumatic air. It has a little electric pump which will take over if pneumatic air isn't available to operate the water system. Okay. A couple other things I'd like to point out on the pressurization pneumatic panel is the high stage light, which indicates that both high and low stage is being supplied to the pneumatic system. This can vary for various aircraft, but generally it happens at the lower altitudes around 77% N2. At the higher altitudes, it'll be slightly higher than that. Above that point, the high stage light will go out and pneumatic air is supplied by the engine only with low stage. And of course, anytime you turn the bleed switch to close, you will force both high and low stage to be closed off to supply the pneumatic. Anytime the pneumatic valve is closed, an amber light will be on, even though, say in this case, that the switch is in the open position. Anytime pressure in the pneumatic manifold is higher than pressure coming from the engine, this valve will close. It will act as a check valve. Now, normally, when you go to start the engine, pneumatic air has to come backwards through this valve, down through the pylon to the starter on the engine. And through the start switch on the overhead panel, it will bypass the check function of this valve. So the light goes out when you operate the starter. In addition, a valve on the starter will operate, and a green light on the overhead panel will indicate the starter valve is open. If this switch is left in a closed position, the engine cannot be started. Also, if you use an APU or pneumatic air and the isolation valve is closed, the engine cannot be started. Air has to come from the source, come down and actually backwards down the pylon to the starter control valve. There is an overheat light above the valve close light, which very seldom would operate. As a matter of fact, if for this overheat light to operate, it would take a dual or triple failure. On some aircraft, the overheat light has been omitted from the airplane. What it indicates is the temperature of the air downstream is excessive, and it would close the valve. Above this, we have our 3 PACs, control valves, and above them the PAC trips. The PAC trip is an indication that something is abnormal with the PAC, and it has automatically shut itself down. When the PAC trip light comes on, the light will stay on and prevent operation of that PAC until the reset button alongside of it is reset. I'll discuss items that will cause the PAC trip in a few minutes. The Gasper fan is for the eyeball outlet in the cockpit and in the cabin throughout the entire airplane. Recirc fans, we have 4 of them. 1 is for the cockpit, 2, 3, and 4 is for the middle, nose and tail of the aircraft, and all they do is circulate air that is in the cabin around so it doesn't stagnate. Normally, the Gasper and Recirc fans are on all the time except the number 1, which supplies air to the cockpit. The switch, when it is on, supplies air of a volume, and it makes quite a bit of noise. Unless it's absolutely necessary, it normally isn't used. The only time it is used is when no air is available from the pneumatic system and PACs can't operate it. It does bring some air to the cockpit from outside. Moving up to the PAC control panel right here, we have the controls for the 3 PACs. The 6 indicators, ACM out, compressor discharge, and airflow, bypass valve, inlet door, and exit door, are controlled by the push buttons. When you have PAC number 1 selected, all 6 of these items are looking at PAC number 1. You select number 2, all 6 of them are looking at number 2. If you push the push buttons to the point that none of them are in, none of the lights are on, all of them are looking at PAC number 1 except the airflow. The airflow will not register at all. So if nothing is selected here, then the bypass, inlet, and exit door and the temperatures will look at PAC number 1. Normally the PACs are operated in automatic. Automatic with these selector switches in the up position. This allows a small computer to meet the demands that are being called for by the temperature controllers above the PACs. We'll discuss that in a few minutes. Normal operation of the PAC, the 3 top gauges run approximately the 12 o'clock, correction, is the 9 position. The bypass valve controls the amount of air that is going through the air cycle machine. In the cold position, it makes the air cycle machine work harder, supplying cold air, and in the heat position, it bypasses the air cycle machine and allows it to run in the idle mode. Normal operation of the air cycle machine is required mostly on the ground and at low altitudes. At the higher altitudes, the air is bypassed, applied to the passengers in the cockpit, is controlled by the inlet and exit door. Now, earlier I mentioned there's 3 things that will cause a PAC trip light to illuminate. Under most conditions, PAC trip indicates a PAC that you normally don't want to operate. The airplane can operate at any altitude with 1 PAC, although the airflow may not be too good and you might have to leave the no smoking sign on. 1 PAC is sufficient to the maximum cruise altitude of the airplane. Normal operation operates with 2 or 3 PACs. A PAC trip will come on with excessive ACM outlet temperature. This occurs approximately 185 degrees. That's very, very hot air, and that would indicate that the pack is not operating on its automatic controls, or there's something wrong with it. The second thing will cause a pack trip would be high compressor discharge. That also trips off roughly about the 12 o'clock position, 425 degrees Fahrenheit, and that would most likely indicate a problem with an inlet or exit door, or the heat exchanger is plugged up. And the third thing that will cause a pack trip is the bypass valve out of sequence with the inlet door. By out of sequence, I mean normally you are operating the bypass valve to control the temperature or the inlet door to control the temperature. If both of them are operating at the same time, that is incorrect, and that would cause the out of sequence to trip off the pack. What is supposed to happen when you're providing air to the cabin, the temperature is controlled by the bypass valve until it reaches full heat. Only when it reaches full heat, then the air is controlled by the inlet door by going from cold or cool towards the heat or closing down. If the inlet door starts moving before the bypass valve is in full heat, then that would say the valves are out of sequence and cause a pack trip. Vice versa, if the bypass valve started going towards cool before the inlet gets to full open or cool, then that would be out of sequence and a pack will trip. Now, technically, I say full, there is a little grace area in there where they can overlap a little, although they normally do not. But when they get out of that limit, you will get a pack trip. My experience on pack trips, most of them are due to the doors being out of sequence, and they generally occur during initial climb, and if you hit the reset, you can get the pack back, because by then the bypass valve is in full heat and the cooling is done by the control of the inlet door. Of course, the troubleshooting procedures in the flight handbook should be adhered to if it's necessary. I might bring out the point that since you don't really need 3 packs, if you're having trouble with a pack, it might be better to operate with a pack inoperative and just operating on the remaining packs than to try to make a pack that isn't working right do the job. Sometimes the operation of the bypass valve in the inlet door, which is controlled automatically by a small computer, doesn't work properly. If that's the case, the pack can be operated in manual. To operate a pack in manual, however, the pack that you want to operate in manual must be selected with the push button. For example, if you want to operate number 2 pack in manual, you must push the push button for number 2 pack and then move the pack selector to manual, and then with the use of the toggle, you can operate the bypass valve and the inlet door. No operation of the exit door is available in manual operation. The disadvantage of this is like manual pressurization. Every time there's a speed change or an altitude change, the bypass valve has to be repositioned and requires quite a bit of attention. Again, the airplane will very nicely do the job on 2 packs, and if you have to operate in manual, it may be better to just leave that pack off. Okay, going up a little higher, we have our 4 temperature controls. These also control a small computer which supply the temperature demanded by each of the aircraft. The 4 areas mainly are the cockpit, the nose section, center section, and aft section of the aircraft. The amount of conditioned air that's going to each area is tempered by a small amount of hot air, which is controlled by a trim air valve. The trim air master switch controls all trim air, and at each area there is a small control valve which adds air to the conditioned air to bring it up to the temperature required for that area. To give you an example, the conditioned air is the size of a saucer. The trim air is the size of your thumb, so it doesn't have too much control. The trim air is straight bleed air off the pneumatic duct, and at least one pack has to be open to get trim air. It's downstream of each of the 3-pack control valves. When selecting the temperatures here, the area that's requiring the coldest air to condition that area will be the controller that is controlling the 3 packs. For example, let's say we had 200 people in the center section of the airplane, and that would be zone 3 that would require the coolest air. The trim air valve for that area would be full cold. That in turn would come down and tell the packs the temperature of the air out of the air conditioning units necessary to control that unit. Now, since the other areas are requiring slightly warmer air, the air to satisfy this, then the trim air will move from full cool to modify that conditioned air for those particular areas. At all times, one of the 4 trim airs should be in the coolest area, and that's the one that's controlling the packs. Generally on the ground, the cockpit is the controlling zone. In flight, zone 3 starts out to be the controlling zone, and it could switch to another zone, probably zone 2, and a long flight. One very important thing I would like to point out: if all 4 auto controllers are in the manual control range, no matter where the trim air valves are, the packs do not have a signal to control the temperature, and they go to the full cold mode. The full cold mode will run the pack to 35 degrees. Now, you can override that by going to manual, but if the occasion arises where all 4 temperature controllers are in manual, the packs will go to the full cold range because they have no input control temperature. Alongside the temperature controllers, we have 2 knobs here for the upper deck heat. Instead of running trim air to the temperature, to modify the temperature of the air coming to the upper portion of the cabin directly behind the cockpit, Boeing has decided to put in electric blanket heaters, and the temperature of those electric blanket heaters are controlled by the position of these knobs. Because generally, if you have 1 pack or no packs on, the airflow will be insufficient, the blanket heater will overheat, and you will get an upper deck overheat light. That light coming on means that section isn't working anymore. You can get rid of the light by turning the switches to off or pushing the reset button. In the same row, we have overheat lights. The overheat lights indicate that the temperature being supplied to the duct is very hot, somewhere in the order of 185 degrees. This condition, though can occur, would be a very, very rare occursion because the packs would trip off prior to getting that temperature. And the trim air does not have much authority above the conditioned air to run it that much hotter. So we do have overheat lights here. They come on at 185 degrees, but the chances of it coming on are very remote. The gauges above indicate the duct supply temperature and the compartment temperature. And of course you would expect the difference between the two to depend on what you're trying to do to the aircraft. For example, if we're on the ground and it's a hot day, you would expect the supply duct temperature would be somewhat cooler than the actual cabin temperature when we're trying to bring the cabin temperature down. However, if we're at cruise and it's very cold outside, then the duct supply temperature would be hotter than the cabin and we're trying to heat the cabin. The Zone 1 duct supply temperature indicator is unique in that you can look at the upper deck in addition to looking at Zone 1s with this series of push buttons here. The upper button connects it to Zone 1, which is the cockpit, and then below it we have two push buttons, upper deck left and upper deck right, which changes this gauge from the cockpit to monitor the compartment temperature and the duct supply temperature in the upper deck area. Now we'll discuss the engine fire detection. This little panel here has given a lot of people trouble in understanding it, and I hope I can make it a little clearer for you. First, we talk about the squib test. The squib test simply sends a small current through the discharge unit, which ruptures the Freon bottle to supply Freon to the engines. And when we do a squib test, all we're assuring ourselves is this unit that fires into the bottle has not been discharged. It does not tell us that the bottle is good. To determine whether the bottle is good requires an outside walk around. On the right side of the pylon, there's two little red discs up there which indicates that a thermal discharge has not occurred. To technically check that the bottle is good, the bottle has to be removed and weighed. Okay, when we do the squib test, we go to the left, we get 4 lights. We go to the right, we get 4 lights. Next I want to talk about are these pointers here. The pointers represent roughly the temperature in the area of the fire detection loop. Normally the pointers lay at the bottom or near the bottom of the scale for all engine operation. If that area starts getting warmer than normal, then the pointers will move up, and generally they move up together as the two loops are side by side and would indicate that other than abnormal temperature there. Usually in the green band, a temperature rising would indicate maybe a minor pneumatic loop leak of air in the engine area. If that leak gets to be of a greater proportion, it could move up into the amber band. The amber band is considered a caution band, and generally if you can't get the temperature pointers to come down into the green band, an engine shutdown is recommended. If the temperature gets to the point where it gets into the red band, then an engine fire warning is activated with a fire handle coming on and the master fire lights coming on. And engine fire procedures should be conducted. Now, that's when everything's working fine. But suppose one of these pointers is inoperative. It isn't working at all. If one pointer goes up into the fire band and the other does not get to the fire band, you will get a fault light with the switches into both positions. That does not necessarily mean there's a fault that is giving you a false fire warning, but you have to go through the engine fault light procedure to determine whether you actually have a fire or a fault. If one sensor is failed and the other goes into the fire band, that will give you a fault, not a fire. It takes, when the switch is in both position, which is normal, it takes both pointers in the fire band to give you a fire warning. Now this was done intentionally to reduce the incidence of false fire warnings. Some aircraft, earlier Boeing aircraft, the false fire warning was probably 9 out of 10 of the fire warning lights coming on, and after a while you got so you didn't believe it. On the 747, if you get a fire warning, you better believe it's a fire, because it's a very, very reliable system. A fault light coming on will also illuminate a fault light in the master annunciator panel on the center instrument panel. One can't come on without the other. When you do a fire test, to get a proper fire test with the switches in both the A and the B has to be moved to the test position to get the fire lights to come on. If you do one or the other, you'll get the fault light and no fire warning. By moving the switches to the down position, this simulates a fault and makes the pointers move to the top of the scale. This will not give you a fire warning, but will give you a fault light here and in the master annunciator. Next thing I want to talk about is the wing overheat. Wing overheat has been one of the more troublesome systems on the airplane. There are numerous sensors in each wing and in the pylons, and what they are primarily looking for is a pneumatic leak at the junction points of the pneumatic system. They are only looking outboard of the fuselage. They are not looking in the center of the fuselage. Generally, if a wing overheat light comes on, say the left one, that would indicate a pneumatic leak in the left wing, and you would have to therefore isolate pneumatic air from going to the left wing by closing the isolation valve and the number 1 and number 2 bleeds. This most times would relieve any pressure and temperature in that area, and the light may go out. However, since it also senses around the bleed valve, it may be upstream of the bleed valve and it may not go out. And then you could reduce the bleed pressure by reducing the engines 1 and 2 one at a time to see if the light goes out. As I mentioned before, sometimes these are faulty and the light comes on when there actually doesn't have a problem occurring. Equipment cooling. A fairly important system. The airplane carries a very, very expensive avionic equipment, and all of it is monitored by this little panel right here. The smoke light indicates there's smoke being generated in the lower portion of the fuselage. It also senses air being drawn across the equipment on the flight deck and the flight engineer's panel and the TR units and the battery charger, etc. Circuit breaker panel. So the smoke light coming on doesn't really tell you exactly where it is, but there is smoke in the air that's being exhausted across the equipment. The no airflow light may or may not come on with the smoke light. They're independent of each other. The no airflow light indicates that the electronic cooling blower is not pulling sufficient air across the equipment to keep it properly cooled. We have 2 blowers. The blowers are operating under all aircraft power operation, and which blower you're operating is selected by the switch right here, a normal position or the alternate position. In the test position, you take power away from the blower and the blower stops. The no airflow light indicates air going past a certain point in this exhaust system. The exhaust system either dumps the air overboard underneath the aircraft, or after takeoff it could divert some of this warm air to the forward cargo. As a matter of fact, the entire forward cargo only heating source is this air. Now there is some air going down along the sidewalls from the conditioned air from the main deck. However, the primary source of heating of the forward cargo is by this air that's going across the equipment. When the no airflow light comes on, if you happen to be on the ground, it will alert the ground crew by operating a horn and a nose wheel. In flight, if the no airflow light comes on, it will cut off all air going to the forward cargo and dump it overboard. We have an override switch here controlling this control valve, which is operated by the no airflow light, manually. In a normal position, as I discussed, the air is dumped overboard on the ground, gradually filtered into the forward cargo as the pressure differential builds up. When the smoke light comes on, the forward cargo supply is cut off, or you can manually move the switch to smoke. However, if this smoke light is on, it's already automatically in the smoke. The third position, ditch, is to close off this hole if water landing is necessary. Of course, if the hole is open, that'll allow the water to come into the airplane and maybe cause it to sink quicker. Aft cargo heat. The test position overrides the normal temperature control and causes the green light to come on. And this is normally done on a cockpit setup, and it should only be held long enough to determine that the valve comes to the open position. Aft cargo heat, as mentioned before, is supplied by pneumatic air on the line between the two isolation valves. In order to do the test, you do not need pneumatic air. The light just indicates whether the valve is operating properly or not. To the left of it, we have an overheat. The overheat is set at a fairly low temperature, somewhere just slightly over 100 degrees. And as we well know at some of the sea level airports on a summer day, the temperature in the cargo hold could easily exceed 100 degrees, so it's not unusual to have the overheat light on the cockpit setup on a very hot day. It would be unusual to have it on a very cold day. When putting the switch to normal, the temperature control will cycle the valve to the open position when it starts cooling off back in the aft cargo. Generally what happens in climb, the light might come on and go out and then come on for the rest of the flight and then go out on descent. Normally in cruise the light is on all the time. If the valve should fail in the normal position, the overheat valve can take over in a cycling function. If the overheat valve does not cycle, then the cargo heat should be turned off. Next control panel is the lower cargo fire protection, and the compartments of the 747 are not totally airtight, but they do have fire extinguishing and fire detection capabilities. The fire detection is done by smoke detectors. They are not temperature sensitive. It's a little photoelectric light on a target, and if the obscuration between the light and the target gets to the point where the light cannot reach the target, then the fire detection activates. Since it is not temperature sensitive, we've had some problems in this area by maybe an insect or a baggage tag causing a fire warning light to come on. There is very little possibility of visually checking the cargo compartments in case of a real fire. Normally the switch is in the off position, and when the switch is moved to the forward position, what it does is arm the bottles for discharge to the forward cargo compartment. It also cuts off the air that's going to the forward compartment in flight. It'd be the same as moving this control valve to smoke. The main reason here is to reduce the amount of air that's going into that cargo, so when you do fire the Freon, the concentration of Freon remains at a high value for a long period of time. We have two bottles to discharge. the number 1 bottle, or the left bottle, should always be used first. That is the large bottle. What that will do will raise the concentration of Freon in that cargo area to the point of keeping a fire suppressed for a minimum of approximately an hour's period of time. However, that will not be true unless the appropriate action is taken with the pressurization in packs. In other words, we have to reduce the flow of air through that area, and we do that by turning off 2 packs and taking a pressure differential to a lower value. The second bottle is a much smaller bottle, and upon an hour of operation, after firing the first bottle, it will bring the concentration of Freon up to approximately what it was when the first bottle was fired. The second bottle may not be sufficient to put a fire out if you fire it first. Because of that, there is a double guard here. First you have to lift up one to get to the first bottle, and then you have to lift up the second one to get to the second bottle. The fire detection test simply overrides the fire warning and causes the fire to operate for each of the test buttons. There's 2 for the forward and there's 4 for the aft. The aft cargo compartment is somewhat larger than the forward cargo compartment because it has a section which is bulk loading. However, the airflow through the forward cargo is somewhat higher than through the aft cargo, so the fire procedures for the forward cargo are somewhat different than for the aft cargo procedures on pressurization. The squib test is the same as the squib test for the engines. It simply checks the power to and through the firing mechanism to discharge the Freon bottles. Now there's only 2 Freon bottles, however we got 4 squibs. The selection of the switch determines which of the squibs are going to be activated. For example, there's a line from each bottle going to the forward cargo area and a line going to the aft. And one squib fires to allow the Freon to go to the forward area. If the switch is in the aft, it would fire the bottle to go to the aft area. One other point I'd like to bring up on the cargo, the airflow through the airplane from front to back through the outflow valves is a good possibility that the smoke in the forward cargo area will end up finding its way towards the outflow valves and eventually may give you an aft cargo fire. In this case, it probably would not be a good idea to fire the second bottle to the aft because that's simply a result of the fire smoke finding its way to the outflow valves. One other problem we've had with the cargo fire detection system is a thermal discharge, not an intentional, but a thermal discharge of either one of the bottles is dumped into the line that goes to the forward cargo area. And if this should occur in flight, what will be the results will be the forward cargo fire warning light coming on, but in addition, the discharge light for the forward cargo light will come on without anybody pushing it. And this would indicate a thermal discharge of either one of the large or small bottles. Now let's discuss the fuel panel. Correction, let's discuss the hydraulic panel. The hydraulic panel consists of electric control pump, temperature gauges, a brake select switch, overheat lights, and the controls for the various pumps. The 47 is very, very unique in that you can have all hydraulic systems activated with the engine shutdown through use of the pneumatic air pumps. The air pumps are not dependent upon engine operation whatsoever. The switch in the auto position will allow the pump to operate whenever it's necessary, and in a continuous position it operates the pump at all times. Generally, in the auto position, it will activate the pump when the pressure drops to a value where it requires aid to bring the pressure back up to normal. And in cruise, normally the engine pumps supply all the hydraulic pressure. However, when activation of a major item, for example, the gear, flaps, or speed brakes, it would cause the air pump to come in and help it. In the auto position, once the pressure is back to normal for approximately 10 seconds, the air pump will automatically shut itself off. The big thing about the hydraulic system is what's on each system. Now, 4 systems are supposed to be totally independent and separate of each other, and what operates each system is relatively easy to remember if you remember one thing. The big items are in systems 1 and 4. The mostly small flow items or flight controls are on systems 2 and 3. And this is reflected in the hydraulic quantity reservoirs. 1 and 4 are somewhat larger than 2 and 3. A good way to remember what's exactly on each system is if you take the airplane and go right down the center of the airplane, the items on the center line of the airplane are generally on system 1. For example, the nose gear steering, the body gear steering, and the inboard trailing edge flaps. Likewise, the items in the wing, the big items, are on system 4, and they would be the wing gear and the outboard trailing edge flaps. Now, there's other hydraulic systems, of course. For example, the brakes. The brakes are normally on system 4, and the entire brake system can be selected to system 1. And on the captain's instrument panel, we have a switch in case the normal brake systems are inoperative. You can switch to the reserve system or system 2. So the brakes are system 1, 2, and 4. Flight controls. All flight controls are operated off of all 4 hydraulic systems. Exactly what flight control is operated by what system can be referred to the overhead panel, and there's a schematic diagram there which we'll discuss when we get to that particular panel. But they're all right there in the cockpit. It'll tell you exactly what operates each system. Stabilizer trim, autopilot, are in systems 2 and 3. And I believe that's it on the hydraulic system. One other area of problems in the hydraulic system is the overheat and the temperature control. The overheat and the temperature control are looking at exactly the same space, same position of the system. And what it's looking at is the case drain lines of the hydraulic pumps. On systems 1, 2, and 3, we have 2 pumps, the air pump and the engine pump. On system 4, we have 3 pumps, the engine pump, the air pump, and the electric pump for ground operation. All of these pumps dump into the same case drain line, which in turn goes to its respective fuel tank, is cooled by running through the fuel tank, and then returned back to the reservoir of that hydraulic system. This is case drain line. The overheat and the temperature are looking at that case drain line. Well, what will make that case drain line fluid hot? Well, it could be Well, potentially it was excessive leakage in the pump. The pump gets old, it gets worn, and fluid is leaking past at a higher than normal rate, would heat the fluid up and cause this to read warmer than normal. The normal temperature generally runs around 45 to 55 degrees. When the fluid going past this gets hotter than that, it indicates something is wrong. Now, also, if there was excessive fluid dynamic flow throughout the entire system, would cause the temperature to go higher than normal. Not that there was excessive temperature at the pump, but the entire reservoir, the system, all its lines and everything heat up. And then adding the case drain temperature to it would cause this to go to a higher than normal temperature. Now, normally the air pump is not operating. If the problem is from the air pump, the temperature would rise when the air pump is running and then go back to normal when the air pump is stopped running. So an intermittent type of problem would probably be due to an air pump. Since the engine pump is running anytime the engine is running, that would show up from an engine pump if the air pump was turned off and the engine pump was depressurized and the temperature didn't come down. Because the only thing operating now is the case drain for the engine temperature. And since it won't come down, that's the problem. Now, if the temperature comes down to normal when the air pump is depressurized and the engine pump is depressurized, then that indicates the problem is in the hydraulic system someplace. Historically, this has been generally due to internal leakage in the flight control actuators. And that would be up to maintenance to find out exactly where it is. However, the system could be depressurized for all except the final phase of flight and pressurized for the approach and landing and written up for maintenance. And of course, if the temperature in zone in the number 4 is from the only when the electric pump was operating, that would indicate that that particular pump is faulty. Quantity test. When you push the quantity test gauge, you drive the gauges towards 0. When the pointer gets around the 6 o'clock position, the low quantity light will come on. One of the problems you should be aware of on this is the quantity test. All 4 quantity gauges are on one circuit breaker, and if that should pop, the gauges freeze in position. However, subsequently, if you should lose quantity out of the hydraulic tank, the low quantity light will still come on when the quantity gets down to the actual value of the 6 o'clock position. So if a quantity light comes on and the pointer looks good, the first thing you ought to go to is see if the quantity test gauge works. If it doesn't work, then you better believe you have low quantity and take the appropriate action. Next panel I want to talk about is landing gear panel. Landing gear panel is a dead panel until you push a button. Normally this panel is not operated unless you have a problem with the indicating lights up front. There are 6 buttons here, and the button pushed activates the particular lights associated with it. For example, the primary and alternate are only associated with the green lights for the gear down and locked. The primary and alternate for the tilt is associated for the 4 wing tilts, which would be on anytime you're on the ground and should be out when the airplane is in flight. And the last 2, the door lights, are indicating for the 5 door lights and indicate that the door is not locked. By holding the gear and the door and cycling the gear, you can tell whether the gear is actually going up or going down and locking. Because of the gear sequence valve, the door must first come open for the gear to move. Then the gear has to be in a locked position before hydraulic fluid is available for the door to close. So if you get the door open light to come on and then go out, then the gear has to move to the other position, either from up to down or down to up. And by monitoring the door lights, you can very easily tell whether that's working, regardless of whether the green down and lock light is working. The tilt lights are poorly labeled. Actually, what it indicates is an untilt light. The gear to be properly stowed in a wheel well must be tilted before it will fit properly. If it is tilted properly, the light is out. If it is not properly tilted, the light will be on. The lights are normally on the pre-flight, and after takeoff, when the weight is off the aircraft, the hydraulic system can tilt the gear and the lights should go out. If you have an untilt light on the primary and an untilt light on the alternate, the gear safety latch will not retract and you will not be able to pull the gear handle up. Okay, moving up to the anti-skid, we have a whole slew of anti-skid lights here, and generally these lights are on when the airplane is parked and the anti-skid is deactivated. Taxiing out, when the anti-skid is activated, all these lights go out. If you have a problem with any one of the wheels with the anti-skid, then the light would come on here, and the light on the master annunciator panel would come on to alert you to this particular problem. Lower lobe galley fire protection is available on some aircraft, and this works very, very similar to the cargo fire detection program. However, there is no controls here to fire any freon in that area. It has to be fought by the flight attendant in that area or have them evacuate. Here we have a potable water system, indicators, and a gauge to tell you how much. Some aircraft have 3 tanks, some have 2 tanks. The amount is averaged by the tank. In other words, this is not one particular tank, it's averaged between all of them. And the hydraulic pressure, or air pressure that's available to hydraulically push the water to the various faucets and coffee makers and somewhat is displayed by this gauge. Their pressure here should be as high as the duct pressure here, and pneumatic air is available. If pneumatic air isn't available, it'll go down to a certain value, and an electric pump will keep that pressure up. However, the electric pump does not put out the pressure of what the pneumatic system does. The flight recorder is normally in the off position with the switch. It's turned, the guard is picked up and moved to the on position to load the flight recorder data. Once that is complete, the switch is turned off and the light comes back on, and the light will automatically go out when you go to aircraft generators, and the flight recorder is active anytime the generators are on the aircraft buses. Well, that concludes the first tape. We'll finish up on the fuel panel and the dump panel on the second tape, and then we'll go to the overhead panel and the forward cockpit panels and the pedestal for the second tape.